tree also we are focusing the binary tree, types of binary tree, and properties, basic of basic components of a binary tree or any tree, and operations. So these things we will cover, and we will cover also the what is a data structure and the linear and non-linear data structures. Okay, so let's start. Okay, let's start. So first we will continue with data structure. What is data structure? Data structure is a way of organize and store the data in a efficient way. Okay, so the searching and sorting become easy. Searching sorting operation become easy. So data structure means we are storing the data in a such a way, in a such a organization. So searching, sorting, deletion, insertion, etc. all the operation become very easy, and memory efficiency will improve. Okay, memory efficiency will improve. So it is of data structure is two types: linear data structure and non-linear data structure. So the linear data structure means the elements are stored in a sequential manner. Okay, sequential manner means like a array, one after another. This, etc. One after another in a single level. There is no level. This is the only one level. They are all connected with the one level. Okay, so single level. While non-linear data structure are the structure which are stored in a hierarchical manner. Okay, these are uh, the linear data structure are stored in a sequential manner, and non-linear data structure are stored in a hierarchical manner. Okay, so one element can connect to the many elements. Okay, in a non-linear, but in a linear manner, the one element can connect up to the two elements, the next and previous. So this is the non-linear data structure. And what are the example of a linear data structure? Array, linked list, stack, and queue. And non-linear are the trees and graphs. Okay, so let's see the what is the these components, key components. So first understand the key components. Okay, key components. Uh, so first is a node. Node contains the data and contains the data and pointers to its left or right child. So let's see, this is the root. Okay, so in root there are the two options. These are the pointers which are pointing to the same node. Okay, root and node. So we can say root and node. Root is a topmost node. Okay, root node is the topmost node of a tree. So the here the data is stored like 5, 3, name, any name, Sachin, etc. So this pointer will point to the next node. Which node? Next node of a right child. So and this pointer is point to the left child node. Okay. So same way it can also pointing to someone like this, and this can also the point, this can also point, and this is not pointing, we can put null here, and this middle portion will contain the key. Okay, key values like 5, 4, 3, like. So these insert the key values. Okay, so the let's define what is this. The node are the data structures uh, which contain data and pointers. So this is a node because it contains the uh, pointer and data. Root node is a topmost node. Child node, these are the child of this. This is the parent and this is the child. So this node is a child of this. This node is a child of this. This node is a child of this. So node that descend from the another node. Okay, so leaf node is means the node, a node with no children. So this is the leaf node because there is no children. This is the leaf node, there is no children. Ancestor means the all nodes on the path from node to root node. So let's see the ancestor of this node. Okay, so ancestor will be the from this node to top. So this come. So these are the ancestor of this node. Okay, for example, again we can see the example. If this are the tree, so I want to know ancestor of this. So the ancestor of this is from root to these nodes. These are the node the ancestors. Okay, so these are the key components. Let's see what is a binary tree. Binary tree is a tree. Uh, is a non-linear hierarchical structure which has at most two children. At most two children. It can be zero children. It can be one children. It can be two. But more than two is not allowed. These are not allowed. So this is the binary tree. So how it is looking? Let's see this structure. So 4 has a two children. 4 is the root, the two children, and 2 is only having a left child, not a right child, but it is not exceeding the 2. Okay, it is not exceeding the number of children is not greater than 2. Here also. So this is the binary tree. This is the leaf tree. If I want to know the ancestor of a one, then these are the ancestor of one. Okay, and this is the right subtree. This is the left subtree. We will see later. Okay, so what are the operations? What are the operations on a binary tree? What are the operation can be done? Insertion of a element. Okay, traversal, in order traversal, pre-order traversal, post-order traversal, level order traversal. Okay, these are the traversal on the binary tree. Deletion of element, searching of element to find height and depth calculation. These are the operations on a binary tree. Okay, so let's see uh, some of the point like hmm, children of a binary tree means this is the root node we already covered. This is the child, this is the right child, this is the left child, this is the leaf node. Okay, these are the leaf node. Again, subtree, subtree of a binary tree. So for this node, this is the subtree. Okay, so subtree with a root 5. So subtree having a root is 5. If I want to subtree of a 5, then these are the subtree. This is the right subtree. This is the left subtree. Okay. So now ancestor of a leaf node. So ancestor and leaf node. Leaf node we already discussed. The ancestor we already discussed. For example, 9 having a 3 ancestor, 3, 2, 4. Okay. So this is already covered. Full binary tree. Okay. So full binary tree means the internode each having two children. Okay, so each node either having a zero children or two children. Okay, either having a zero children or two children. For example, 4 is two children, 9, 2 having a two children, 9 and 13, and 9 having a zero children, no problem. So 5 is having a two children, 7 and 6, and 7 having a no children. So this is the full binary tree. Okay, so full binary tree means the tree which have which full binary tree means the binary tree which having a zero or true childrens. Okay, one children is not allowed, more than two children are not allowed. Okay, complete binary tree. Complete binary tree. Complete binary tree means a complete binary tree means the binary tree from the complete binary tree is display specialized from the binary tree where the all levels are filled completely except the last, possibly the last level, which is filled from the left to right. Okay, so it means what? All levels are filled from left to right. Okay, left to right, and last level may be the filled or not. So let's see the example. If these are the elements, let's say 4, 2, 5, 3, 6, 7, 14. So okay, and let's see, uh, 4, 2, 5, 3, 6, 7, 14, and 13, 5, and 9. So let's see, fill this one by one. So we make its root node, and this is the left, this will be the right, and this will be the left of this will be the right of this will be the left, this will be the right. So we are filling from the left to right for each level. We are filling left to right for each level. So this is a complete binary tree, and complete binary tree is also called almost complete binary tree. Why? Let's see. If we are filling these elements 4, then 2, then 5, 3, 6, 7, 14 from left to right, and 13, 5, 9, 13, 5, 9. So we are from left to right. Let's see this, uh, the this portion is not filled. There is no children of a 7 or 14. So we can say the last level is not completely uh, filled. So all the levels of a tree except the last possible one are filled. If the last level is not completely filled, okay, if the last level is not completely filled, it will filled from left to right. It will fill from left to right, ensuring that nodes are positioned as far left as possible. Okay, so this is the complete binary tree. So it is ensuring that nodes are uh, positioned as far left as possible. So we are filling with left to right as possible. Okay, so this comes under the complete binary tree. So if the new node is inserted, means let's see, there is a 20. So if we want to insert the 20, then it will insert at here. If there is a 3, so it will there is a 31, it will insert at 31. Okay, this this way. Okay, now perfect binary tree means what? A perfect binary tree means a binary tree is a type of perfect binary tree is a type of binary tree where the all the leaf nodes are at the same level or the same level, and number of leaf nodes is maximized as for that level. Okay, so means what? The all the leaf nodes are at the same level, and fill the this tree maximum leaf nodes with the maximum leaf nodes. So at level 3 maximum leaf nodes can be the 4 now, all are filled. So this is the perfect. At level 2 all the leaf node can be the 2, so it is filled with 2 maximum leaf node, and all leaf node are the same level. Why same level? Let's see this example. So for in this example, this is also leaf node, and this is also leaf node, this is also leaf node, but they are not at the same level. So this is not a perfect binary tree. So valence binary tree. A valence binary tree is a type of binary tree where the height of a two subtree of any height of a two subtrees. We are checking the height of a subtree is differ at most one. At most one. So this property ensures that the trees are relatively well balanced. Okay, so it is preventing the tree from the becoming highly skewed or degenerated. So the height of a subtrees. So this is the root, this is a subtree, and this is a subtree for this. So the height of this right subtree and left subtree is differ at most one. Differ at most one. So difference of a height of this and this can be at most one. Okay. Let's see the example. In this example, let's consider this. This is the root. This is the left subtree, and this is the right subtree. This is the right subtree. This is the left subtree. Okay. So if I will check the height of this, so height is for this 1, this is 1, 2. So height of a left subtree is 2. Height of a right subtree is 1, 2. So 2. So the difference between the left and right will be the 2 minus 2 is 0. So it is a balanced. Okay. Let's see this example. The height of a subtree of a 4 is left subtree of 4 is 1, 2 maximum. So 2. The height of a right subtree is only 1. Only 1. Okay. So difference in uh, the height of a left subtree and right subtree is 2 minus 1 is 1. So it is also balanced because at most 1 is allowed. Okay. So this is a balanced binary tree. Okay. So we can say this is a avian tree also. Another name of this tree is avian tree. So let's see the another example of this. So for if we check the height of a 4 it is 4, it is a valence or not. So let's see the left subtree height and right subtree of a 4 node. Okay, for this node. Okay, we are checking. So left subtree height is 1, 2, 3, 1, 2, 3, 3, and the right subtree height is 1. So the difference is at most 1. So at most should be the 1, but difference is it is not balanced. Not balanced binary tree for 4 node. If I will check for a node 2, if I will check for a node 2, okay, for node 2, the left subtree is this and right subtree is this. So let's see the height of a for node 2. So left subtree height is 1 and 2, 2, and the height of a right subtree of a node 2 is 1. This. So the difference is 2 minus 1 is 1. So it is a balanced. So for node, if node 2 is a root node, it is a balanced. But for a node 4 is it is not balanced. Okay. So it is a overall it is a unbalanced if we check. Okay. Degenerated binary tree means the binary tree which is either going on a left side or right side in a leaning way. Okay. So if I will put a let's see the 1, 2, 3, 4, 5, 6, 7, 8. Okay. If I will put this in a binary tree. Okay. In a binary tree. So the node is a root node. So 2 is greater than 2, 1, and 3 is greater than 2, and 4 is greater than 4. Like this way it is going right side. Okay. So this is the generated tree. Yes, if we put if this is a root node, then 7, so it is going left side. So this is the degenerated binary tree. Okay. Level and height. Okay. So level means if this is a root node, so level for a root node is 1. So level is start from the starting level 1, 2, 3, 4. But height is for this root node is 0, and we counting with the age. So height is 1 for this level, and height for this is 2, and this is for 3. Okay. So we can see that. So level equals to uh, height plus 1. Okay. Always. Or height is equals to level minus 1. If level is 4, height is 3. So let's see the what is now if we count the number of nodes in this. full complete binary tree. So number of nodes is equals to the 2 to power h plus 1 minus 1. Okay, so and because this is the same, so if we count the number of nodes in the terms of label, so number of nodes equals to the 2 power h minus 2 to power l means label minus 1. Okay, so this is